All right. Buddy, audio going? Yep. All right. So for homework 5, part B, derive algebraically the amplitude ratio and phase lag for a proportional integral, otherwise known as PI controller. Explain why a first-order system with the PI controller will always be stable, whereas a second-order system or a first-order system with a time delay may not be stable for some control parameters. All right, so a lot of this is going to tie in directly with this principle that we proved on part A, and then this principle, right? Or I guess these two right here for what's going on with the time delay for first order. All right, where's my, here we go. All right, so let's get into what a PI controller is. So for most of what we've been working with, we've had a very basic proportional controller. Which has just been KC, and then we multiply that by some kind of area. But what we're doing with a integral controller is we take our KC and we multiply it by the area, but then we have our error. We take the integral of that from 0 to, we take the integral of that with respect to t from 0 up until whatever time we're looking at for however long our system's running. That's how long it's going to accumulate error. And then that's all multiplied by our reset time. Or I guess the inverse of the reset time, the tau I is called the reset time. I'm not sure if this 1 over tau I is considered the reset time or if it's considered the inverse. But what we do from here is once we want to put this into our system and into the Laplace domain, we'll go ahead and Laplace transform this. So we'll get KC. We get Laplace transformed error. And then the Laplace transform of any integral is, first of all, we have the reset time on the outside. Then it's that variable that's being integrated over S. So we pull our error out, have KC times 1 plus 1 over tau IS. This right here is our new GC that our Laplace error is being multiplied by. So this is our new, our new GC. So what we want to find is the amplitude ratio, and the phase lag. So amplitude ratio, just like any other, is square root of our real part squared plus imaginary part squared, and then the tangent of the phase lag is equal to our imaginary part over our real part. So we want to find both of these. So we'll go ahead, we'll start working with this. So we will take our GC and we'll input I omega for our S as we always do. So KC times 1 plus 1 over tau I omega. All right, so we go ahead and multiply the top and bottom of our fraction by I. So then that turns -1 times I tau omega. So our -1 over tau omega is our imaginary part, and then 1 is our real part, right? And then both of those are multiplied by Kc. For our amplitude ratio, the Kc is relevant, so it gets squared, and then it's square rooted, so we can just pull it out to the front. And then we have 1 plus 1 tau omega, and those are squared on the bottom. You can simplify this further, but I actually think it looks fine how it is. So that's our amplitude ratio. And then for our phase lag, so tangent of phi equals our imaginary part, so -1 over tau I omega. Oh, also, in case I forgot the I on any of these taus, they're notated as tau I. It's not the same thing as the tau that we have on our transfer function. I forget. It's not the system gain. I forgot what that's called. But tau I is our reset time. For 1. So our phi phase lag is equal to tan inverse 1 tau of, negative tan inverse. No, phi is equal to negative tan inverse of 1 over omega. 1 tau I omega. Goodness gracious. That's this right here. Okay, so to answer our question, so we got the amplitude ratio and the phase lag. That's good. So why the PI system, why a first order system with a PI controller will always be stable? So like we showed earlier in part 1 of part A, when you have these in series, and it's also, so since we're running this along with in this example, a first order transfer function, the phase lag of this is simply going to be added to the phase lag of whatever's going on in our first order transfer function. And we know that our first order transfer function is never, the magnitude of that is never greater than 90. And for certain parameters, so let's say we wanted to make our phi as, the magnitude of our phi as big as possible. We would make, the one thing that we can adjust would be, or I guess what we would adjust would be our tau I. And if we wanted to make that, let me focus. We want to make that as close to 0 as possible. And that means that the term inside our inverse tangent would be basically as close to infinity as we could possibly get, which means that we would get the biggest value from our inverse tangent, which would be, or the biggest value from our inverse tangent, which would be 90, and then of course it's multiplied by -1, so we would get -90. It doesn't quite reach -90. It gets as close to it as possible, and same deal with the first order system. So let's say both of them are as close as possible to 90 as we can possibly get. As we showed in part 1, we would add those two phase lags together and we would get as close to -80 as we could possibly get. Thing is, anything past -80, that's where we would reach instability. So since we're not actually getting to 180, we don't have to worry about the system becoming unstable. However, with our second order, that's not the case. If we were to make this as small as possible, we'd be adding -90, and that would put our second order over 180, and then we would start running into instability. And the same principle goes for our time delay, because we showed back in part 4 And we showed in part 5 that the time delay can basically just go to negative infinity. So regardless of what you're adding with this inverse tangent, the time delay will still mess up even a first order transfer function. So this should be our last part. Oh, shoot. There we go. Okay, so this should be our last part. For a first order process with a time-dependent model, or a time delay model, with the gain of 1. So k is 1, time constant of 1, and time delay of 1, so theta is 0.1. Determine the optimal PI controller and reset time using the integral time weight absolute error criterion. So that's going to be determined by this. This is the integral of the time weight absolute error. We're using a set point, obviously, and then we're using a PI controller. So we're going to use these 4 parameters. But first, let's just go ahead and simulate what our system is. So we, of course, have our GC, a GP, and a GM. Luckily, the GM is 1. That is the easiest. All right, so first we have our GC. So that's going to be KC times 1 plus 1 divided by tau I times 2. Times S, I mean. So that's our GC. GP is going to be K, so it's just a first order process. Yeah, so it should just be K. I'm not blanking what a first order process is. It's up here. Oh, there's also a time delay, so I totally would have forgot about that. All right, first order. And we want this in terms of S's, and we'll see why. Tau S, theta S, and GM is 1. All right. Then our overall process, we can call that FD. It's going to equal our, I guess, what is it, closed loop, where it's just the first part, and then on the bottom is 1 plus basically everything. So we have GP times GC divided by, close but not quite, times GM, although I guess GM doesn't matter. And then we'll want to simplify this. So GFB equals simplify. How is it typed in up here? Import simplify. There we go. Let's see. It's been running slow on me, so let's see what's going on. All objects has no attribute. Oh, do we have to run? What in the world? Is this not ran? Okay, let's see if that does anything. In the meantime, we'll go ahead and we'll put in our Baudet command, because that's why we're going to need everything in S. So I'll just use 1, and then our amplitude ratio, or omega, it's going to equal Baudet, although that's not quite it. It's not GFB. It needs to be GC times GP times GM. What's going on? No callable. I don't know what that means. Let me go ahead and write out. No, I guess we'll pause here and then come back. Okay, so because we're running this in a different method other than the normal numerical simulations that we run, this is not supposed to have the NP in front of it, and for some reason that was messing everything up. So we're good right there. All right, so we can plot this. So I'm going to steal these. This fig 5. Then we're also going to want to run a simulation of this. So we're going to want time to be 100. Oh, perfect. All right, let's run these two. Oh boy. How does this turn out? Okay, so that's looking. Yeah, so we have a step change of 1. That's what we want. Why this is not behaving, I'm not entirely sure. Phase. Oh gosh, that's supposed to be phase. Okay, I don't know why having that messed up the other one. Okay, so we do get to our set point, but it takes, how long does it takes about 3 seconds. Is this recording? Yeah. Okay, so it takes about 3 seconds. So we're going to try to figure out a value for reset time. And then also, I think KC, that gives us the most optimal controller gain. So again, that's determined from this. So these are our parameters. It's going to be, so our PA is going to equal point here. Oh gosh. I'm gonna lose my camera for just a second. PA is going to be equal to 0.586. P is going to be equal to negative 0.916. IA is going to be equal to 1.03, and IB is going to be equal to 0.165. All right. And let me. Can I copy? No, I can't copy and paste this. Let me quickly write out the formula for that. So that's going to be y equals a theta divided by tau is to b or y is k times kc mode All right, I'll be right back while I get straightened out with this. All right, there we go. Yeah, it was going to take me a minute to get these written out, and I had to figure out how to set up my display properly. Okay, so for design relation, I'm going to be using these. So that's going to be our PA, and that's raised to the power of PB, and then tau I is going to be equal to do some algebra right here. So tau divided by IA plus IB times theta divided by tau. So then Kc would be all of this divided by K. So let's bring this. Double check that's correct. Y equals this star. A plus IB theta divided by tau. And okay, yeah, I think that should be correct. So we'll get rid of, I guess not get rid of, we'll do the same thing to these. We have new values for these. Did that run correctly? Okay. All right, and then I think this should get us to our set. Oh, no, that does not get us to our set point faster. What do we mess up on? K tau theta. Oh, that has us go all over the place. All right, we'll be back. All right, I found out where I went wrong. First of all, I forgot the negative on this, so that's going to make a big difference. And then I had a copy and paste issue with the K. I was using lowercase k, which would have been the k all the way back up here, which was 1 over b. And we don't want that. Oh gosh, there we go. So let's run this now. Okay. So yes, we get to our set point much faster than we did before. I think last time it took us about 3 seconds to get there, and this is taking us about a little over half that time, but still a lot faster. But yeah, I think that wraps up Process Dynamics Homework 5, which wraps up the Process Dynamics class.